So we're going to start off with a little bit of vocab for our radicals here. So in a radical, you always have that right there where you got the actual radical sign. You've got this little n out in front, which means that's your index. That tells you what root you're looking for, whether it's your square root, your cube root, your fourth root. That number out in front tells us the index is what they call it. It's your root. What are you looking for? And then underneath your k value is what they refer to as your radicand. Sometimes that's your perfect square number. Sometimes that's your perfect cube. Sometimes it's not a perfect square or perfect cube, and you have to be able to break it down still. So again, this symbol itself, that is what the actual radical is that symbol over there. So we would read this notation right here, n square root k, we read that as the nth root of k. So if there was a 2 there, it would be the second root of k. If there was a 3 there, it would be the third root of k. Now, if there is no number written out in front, like in this one, in number 1, that's always going to be a 2. If there's no number there, it's because they mean for it to be a 2. They don't always write the 2. So this just means to find the square root of 16, which we know to be 4. Over here in number 2, they want us to find the fifth root of 32. Now, not everybody knows that one off the top of their head, so we're going to use our calculator to help us. So when we want to do fifth root, what you want to do is you want to type in the 5 because you're looking for the fifth root, so we put that number in first. You go to your math button, and you want choice 5. It's got the x out in front because that's meaning you can make it any root. So we hit choice 5, and if your calculator's updated like mine, it'll actually put the 5 as that little index number out in front, just like you're used to seeing. And then you type in your 32, and we enter. So the fifth root of 32 is 2. So next one, they want the negative fourth root of 81. So again, go ahead, use your calculator, find the fourth root of 81, type in the 4 first. Go to your math button. So 4, math, choice 5 of 81. Oops, I hit the cube root. 4, math, choice 5. There we go. 81. And we get 3. But it should be a negative 3 because it had that negative sign out in front of that radical. So next one, third root of negative 27. Go ahead, type that in your calculator. Let's see what we get. The third root of negative 27. Did anybody do that one yet? What do we get? Negative 3. Now, you cannot always take this radical sign of a negative number. It works for this one because it's an odd index number. It doesn't work. Like, you can't take the square root of negative 9. That's going to get into a couple lessons from now how we deal with that. But for now, you can't do that. So let's take a look. If we have fractions under the radical, what our little diagram up here is telling us to do is to separate it into just the top and then just the bottom, and then simplify it from there. So looking at our first example, we got plus or minus the square root of x squared over 16. So I'm going to separate this into plus or minus the square root of x squared over the square root of 16. So you separate from top from the bottom, give them each their own square root sign. So again, our answer is still going to have that plus or minus out in front. That's not going to go anywhere. Yeah, the square root of x squared would be x. Square root of 16 would be 4. So we get plus or minus x over 4 is our answer. Alright, so number 6, again, let's separate it. So we got square root of 25 over the square root of 9. So the square root of 25 gives us 5, and the square root of 9 is 3. So we get 5 over 3. And then 7, even though it is a third root, we still do it the same way. So we want the third root of negative 8 and the third root of 27. What'd you get? Mm-hmm. Yep. -2 over 3. Again, you can use your calculator to help you with that one. You can do your third root in there. Now those ones all worked out well because those were perfect squares and perfect cubes. It's not always going to be that way. So how do we simplify the radical when it's not a perfect square or a perfect cube? What we need to do is we're going to separate them into two radicals. We have to find the largest perfect square that goes into the number. That's going to go in our first radical, and then what's left, as I call it, goes in the second radical. Yes. So this is when your little charts that we just made, these are going to come in handy because then you can see what your perfect squares are, see if they go into the number. So as we just said, 36 is the largest perfect square that goes into 72. So 36 is going to go in our first one. If I divide 72 by 36, I get a 2. So that goes in my second radical. So now 36, as we said, is a perfect square. What's the square root of it? So that comes out as a 6. 2 stays under the radical because we cannot take the square root of a 2 because it's not a perfect square. It would be this long, never-ending decimal. So 6 square root of 2 is our answer. Let's try number 3 before we get to number 2. So number 3 wants the cube root of 24. So even though it's a cube root, we still follow the same steps that we just did. So we're going to set up our two little radical signs with our little 3's out there. So we're still doing cube root. And we got to find the largest perfect cube that goes into 24. So take a look at your list. What is going to be the largest perfect cube that goes into 24, you think? Yes. So if we look at our perfect cubes, 8 is going to be the largest one. 8 goes into 24. So 8 goes in the first one. And then I put a 3 in the second one because it's 8 times 3. That gives us 24. Cube root of 8 would be a 2. And then the 3 stays underneath that cube root because you can't actually take the cube root of 3. It's a decimal that goes on forever. So 2 cube root of 3 is our answer. So going back to number 2 now, you can separate it when you have variables also. So when you have variables, what needs to happen is the exponent needs to be divisible by the index. So again, our index here is a 2. It's not written, so that means it's a 2. They generally don't write the 2. So my exponent on my a has to be a number that's divisible by 2. But I can't actually divide 7 by 2. I would get a decimal. So we would separate this into a to the 6th and a to the 1st. Because if you add your exponents, you still have your 7. But I can divide 6 by 2, so that makes that a perfect square. And then you put what's left in the other one. So then if we look at our b, we have b to the 20th. Can I divide 20 by 2? Yes, so that's already a perfect square. So I'm going to put my b to the 20th in our first one. That's our perfect square one. So now, again, as I said, to take the square roots, you have to divide your exponents by the 2. So that gives us a to the 3rd, b to the 10th, and then that a to the 1st stays under the radical. So that becomes our final answer, a to the 3rd, b to the 10th, square root of a. So if we look at our fourth one, again, same rules apply. I'm going to set it up to start breaking it apart. So let's look at each piece. Is 27 a perfect cube? Yes, if you look at our list, 27 is there. So 27 is going to go in my first one. That's already a perfect cube. Can I divide 8 by 3? No, we would get a decimal. So I'm going to separate that into x to the 6th and x squared, because I can divide 6 by 3. And then I put the other 2 that's left to make it an 8 in the other radical. And then can I divide a 3 by 3? Yes. So y to the 3rd is a perfect cube, so that goes in the first one. So now let's take the cube root. So the cube root of 27 would be 3. Divide my exponents by 3, so 6 divided by 3 gives me x squared. 3 divided by 3 gives me y to the 1st. And then I still have that cube root of x squared coming along after it. So that becomes our final answer for that one. Alright, let's take a look at the last one on this page. So we got this 2x squared y out in front that I'm going to still leave out in front. And then I'm going to set up my two radicals so I can simplify. So we're dealing with square roots because we don't have an index written there, so it means it's a 2. So what's our largest perfect square that goes into 50? 25. And then we put a 2 there because it's 25 times 2 is what gives us 50. So then looking at my x, I have x to the 7th. 7 is not a perfect square as far as exponents go. So I'm going to separate that into x to the 6th and x to the 1st. So again, if you add those, I still have my 7. And then y to the 10th, 10 is divisible by 2, so I can keep that as y to the 10th. I don't need to separate it. So now, keeping my 2x squared y, I'm going to put a little multiplication dot there because I'm going to multiply it times the stuff I take out of the radical. Square root of 25 is 5. Divide the 6 by 2, I get x to the 3rd. 10 divided by 2 gives me y to the 5th. And then I still have the square root of 2x after it. So this one just had that one extra step because it did have the stuff out in front. So now we need to multiply 5 times 2, 2 times 5 gives us 10. Adding our exponents, so x to the 2nd times x to the 3rd would be x to the 5th. And then y to the 1st times y to the 5th would be y to the 6th. And then we've got our square root of 2x after it. Okay, adding and subtracting radicals is very similar to adding and subtracting your x's. You can only add and subtract those if they're like terms. So like for example, I could add 2x plus 3x. And that would give me a 5x. You just actually add the numbers out in front. You keep your x as an x. But we couldn't add a 4x squared plus a 7x because those are not like terms. They have different exponents. It's very similar as far as your radicals go. You can only add them if they have the same radicand, which again, remember, that's your number underneath the radical. So if we look at our first example, we have a 27, a 3, and a 12. I can't add those yet because those are not the same. They need to be the same in order to add them. So what we need to do is we need to do some simplifying. So let's simplify our 5 radical 27 first. What's our perfect square that goes into 27? 9 and 3. I heard somebody say them. So now the square root of 9 is 3, and I still have that radical 3 under the radical there. And I got to do it times the 5, so when we simplify it all together, I get 15 radical 3. Let's look at our next one. 4 radical 3. Well, I can't really simplify anything with that because 3, there's no perfect square that goes into it. So that's going to stay as minus 4 radical 3. I'm just going to bring that down. So I just brought that one down there. Looking at the 12, yep, I know a perfect square that can go into 12. What is it? 4. So 4 and 3. So the square root of 4 is 2. And then times that other 2 that was already there, that gives us a 4 radical 3. So now if we look underneath our radicals, those are all radical 3s. Now we can combine them. Yep, because 15 minus 4 would give us 11, plus 4 would give us 15 radical 3. So that ends up being our answer. So we added and subtracted the numbers out in front, and we kept the radical 3 as radical 3. That didn't change when you add and subtract. So let's take a look at example number 2. We can't combine it yet because we don't have like radicals. So I'm going to set up to simplify the 18x cubed first. So dealing with just the 18 for now, what's our perfect square that goes into 18? 9. 9 and 2. And then x cubed, we're going to break up into x squared and then x to the first. Because x to the third is not a perfect square. It's got to be an even exponent for perfect squares. So now for 9x squared, when I take the square root of it, that turns into 3x. My 2x is still underneath there. And I got that 5x out in front that I need to multiply times my 3x. So 5 times 3 gives me 15. X times x is x squared. And then I have the square root of 2x after it. So 15x squared, radical 2x. Alright, let's simplify our other radical that we have there. So I know this is going to be a minus. 36 and 2. X to what exponent is going to go in the first one? What's the largest even? 4. So x to the fourth, and then our x to the first. So then our square root of 36 is 6. Divide your exponent by 2. And we still have radical 2x after it. So now we can actually subtract because we have the same radicands. So 15x squared minus 6x squared would give us 11x squared, square root of 2x. It would be 9. Yeah, good job. Nine x squared, square root of 2x. So adding and subtracting, you have to have the same numbers under the radicands. Multiplying, though, that rule doesn't apply. You don't have to have the same number under the radicands in order to multiply. So when you multiply, as I have written here, you multiply the numbers out in front, so your coefficients, you multiply those, and then you multiply your radicands underneath, and then we simplify. So our simplify is going to come at the end for your multiply. So, first example, negative 2 times 3. Multiply those numbers out in front. That would give us a negative 6. Then you multiply your numbers underneath. So 3 times 6 would give us 18 under the radical. Since I multiplied the numbers under the radical, that answer is also under the radical. And so now we simplify. What's our perfect square that goes into 18? 9 and 2. 9 comes out of the square root sign as a 3. 2 stays under the radical. And I got to multiply that 3 times that negative 6 that I had out in front. So our final answer is negative 18 square root of 2. So number 2, we're dealing with cube roots, but it still follows the same things. Multiply your numbers out in front. Out in front of here is a 1 that we don't always write, so 4 times 1 gives us a 4. Then I'm going to bring my cube root sign. And then I got 16 x to the 6th, following your exponent rules. X to the second times x to the fourth would be x to the 6th. You add those exponents. So now we'll simplify. So using your chart on the back of your cover if you need to, what is our largest perfect cube? That goes into 16. 8. So I'd put my 8 here. My 2 goes in the second one because 8 times 2 is 16. And then can I divide my exponent of 6 by 3? Yeah. So that means that's a perfect cube already. I don't need to separate my x's. So it's just going to be x to the 6th along with my 8. So I'm going to keep my 4 out in front. The cube root of 8 is a 2. Again, divide your exponent by 3, so that becomes x squared. And then we still have our cube root of 2 there. So now just multiplying your stuff out in front, 4 times the 2. We get 8x squared cube root of 2 as our final answer. Our third one there, 7 square root of 3 squared. What that means is just write it twice and then follow your multiplication rules. So 7 square root of 3 times 7 square root of 3. So our rules tell us multiply the stuff out in front. So 7 times 7 would give us a 49. 3 times a 3 gives us the square root of 9. Now we don't have to do the 2 radical signs here because 9's already a perfect square. It's already what we're looking for. What is the square root of 9? 3. So then we just have to do 49 times that 3. 147. So that's our final answer for that one, 147. So taking a look at our fourth one, we have a binomial times a binomial. We've done this before. So we're going to have to take the 3 and distribute to both terms in the other parenthesis. So my 3 times my 4 gives me a 12. My 3 times my negative radical 5 would be negative 3 radical 5. There was no radical with the 3 to multiply, so you just did that 3 times that 1 in front of it. So now we have to distribute our other radical 5. So radical 5 times 4 would be 4 radical 5. And then radical 5 times negative radical 5 would be negative radical 25. So then what does the square root of 25 turn into? 5. So then we're going to cross that out, make that a 5. So now combining my like terms, 12 minus 5 gives me a 7. Negative 3 plus 4 gives me a positive 1 radical 5. So that ends up being our final answer. Alright, let's try number 5. So we got 2 radical 3 plus 1 squared. So that means it's going to be 2 radical 3 plus 1 times 2 radical 3 plus 1. You got to write it twice. And now we're going to multiply just like we did for number 4. So I'm going to distribute 2 radical 3 times 2 radical 3. Multiplying out in front gives me 4. Multiply underneath the radical gives me 9. So 4 radical 9 would be our first term. 2 radical 3 times 1. That would just be 2 radical 3. So then distributing our 1. 1 times 2 radical 3 is another 2 radical 3. And then 1 times 1 gives us 1. So let's clean this up and combine our like terms. For our first term here, the square root of 9 turns into a what? 3. And then times that 4 that's out in front of it gives us a what? 12. So that turns into 12. Yep. So for our final answer, 12 plus 1 would give us a 13. And then 2 radical 3 plus 2 radical 3 would be 4 radical 3. Remember from up above, you keep the radical 3 the same when you're adding, you just add your numbers out in front. So 2 plus 2 gives us 4. Alright, so I want you to take a minute, try number 6 on your own. Try multiplying out, and let's see what you get. So we should end up with a 1 for that one over there on number 6. And as I walked around, I saw that most people had that one. So when we distributed the 2, we had a 4 plus 2 radical 3, and then we distributed our negative radical 3, so we got the negative 2 radical 3 minus your radical 9, which turned into a 3. I crossed it out and made it a 3. And then these ones canceled each other out, because you had one positive, one negative. Positive 2 minus 2 would give us the 0, so that's just gone. So it gives us 4 minus 3, which was 1. So now down here, this little note here, this is me just trying to help you make things go a little bit faster. If you can memorize these little rules, then it'll help you multiply things out faster. So instead of taking something like this that's squared and writing it out twice like we were just doing, you could kind of memorize this pattern to it, that it's x squared plus 2xy plus y squared. So that means you take your first term and you square it. You multiply your two terms together and then times a 2, and then you square your last term. And it's kind of like a little fast hand if you can get a hang of it. So like if we take a look at this example here, x plus 9 squared. Trying to use this for a moment, the little note up there. Again, following the rules, it's saying to take the first term and square it. So our first term is x. So that would end up being x squared. Your middle term means you multiply the two of them together and then also times a 2. So x times 9 would be 9x times 2 would give us an 18x. And then for your last term, it's the other term squared. So we did the x squared first, so now it's going to be the 9 squared, and that would give you an 81. So as I said, it's just kind of like a faster way to get you to multiply if you want to use it. You don't have to, though. Yes? Yes, that ends up being a trinomial, and it's actually what we call a perfect square trinomial. Yeah. So if we try the next one, x minus the square root of 5 squared, that's going to follow this rule down here. So let's just give it a shot, see if we can do it. So again, first term squared, so my first term is x. So I'm going to square that, so x squared. Your middle term, this time because it was negative here, is going to be negative 2 times the two of them multiplied together. So x times negative square root of 5 is negative square root of 5x, or you could put the x out in front. And then we would have to do it times 2. So it's the 2 times the first term times the second term, multiplying those two together. And then it's plus the last term squared, so radical 5 times radical 5 would give us a radical 25, which that turns into 5. So we would get x squared minus 2x radical 5 plus 5 is our final answer. Again, if this just confuses you more, then you don't have to use it. I'm just trying to help you make things go a little faster if it works for you. So then our other little trick that we have is if you have the same two terms, the only difference is one is minus, one is plus. Like our example 9 here. You have square root of x, square root of x, and then you have a 4 and a 4. So you got the same two terms in each parenthesis, just one's plus, one's minus. All you have to do is multiply the first two together. So that would give us the square root of x squared. And then it's going to be minus the last two multiplied together. So that would just be minus 16. Because what would end up happening is since one's plus, one's minus, is any middle term you have is going to cancel each other out. Because you're going to have the negative version of it, then you'd have the positive version of it. They end up canceling each other out. So then we just have to clean this up a little bit because we can't leave that as the square root of x squared. That would give us x minus 16 would be our final answer for that one. So again, if they don't work, that's okay. If they work, go ahead and use them. So it's all entirely up to you. Let's take a look at our last part. Dividing. Now when it comes to division, you kind of very rarely ever actually divide the two radicals. Like this one, you're going to do what we did up on the front. Separate it in so that the top is its own radical, the bottom is its own radical. So what's our square root of 121? 11. Square root of 9. And there we go. So one's like example number 2. You can try dividing first. Can we actually divide a 90 by 18? Use your calculator. Let's check. 90 divided by 18. Does it work? Yes. What do we get? So kind of like our multiplying rules, if they actually divide, then the numbers that you divided under the radical, that answer's still under the radical. And then you got the numbers out in front, so that's just 2 radical 5 there. Now sometimes when they don't divide, you have to do what we refer to as rationalizing the denominator. So like in example number 1 here, I can't divide a 2 by a square root of 8 because they're not both under a radical. So what we need to do is multiply the top and the bottom times that radical. This is what we call rationalizing our denominator, getting that radical out of there. So when we're multiplying, you multiply your tops. 2 times radical 8 would just be 2 radical 8. Radical 8 times radical 8 would be the square root of 64. Which, what is the square root of 64? 8. Has anybody seen the pattern with that? Any radical when it's times itself is just that number underneath. Square root of 3 times square root of 3 gives you the square root of 9, which turns into a 3. So if you multiply any radical times itself, it's just that number underneath. Alright, so we still have to finish cleaning this up a little bit. Because the square root of 8, there is the perfect square of 4 that goes into it. So we've always got to simplify if we can. In this case, we can. The square root of 4 comes out as a 2, which times that other 2 that's already there gives me a 4 radical 2 over 8. And then can I reduce my 4 and my 8? Yeah. What can we divide them both by? 4. So that would become a 1. That would become a 2. So you could have 1 radical 2 over 2. Sometimes you might see that written on the regions as 1/2 the square root of 2. Those are the same thing. So let's take a look at our second one. So let's separate these first. So I have the square root of 7 over the square root of 5. I can't simplify those. There's no perfect squares that go into 7 and 5. I can't divide those two numbers together, so we need to rationalize the denominator. Which means I'm going to multiply top and bottom times that square root of 5, because that was the number in the denominator that we're trying to get rid of. So for the top, 7 times 5 would give me the square root of 35. And as I was just saying, radical 5 times radical 5 gives us just what? 5. And then I can't divide those. I know a lot of people are probably thinking, well, you can actually divide 35 by 5. And you can. But in this case, you can't because 35 is under the radical. 5 is not. So you can't actually divide those. All right, then we got 2 more. When we are rationalizing our denominator and we have a binomial down there, like we do right here in example 1, we have a binomial. We have the 5 plus radical 3. We still can't have the radical 3 down there. That's still not okay. We have to rationalize it. So when we rationalize it, we multiply it times what we call the conjugate, which is just the same thing, only you change the sign in the middle. So my 5 plus radical 3, I'm actually going to multiply the top and bottom times 5 minus radical 3. I'm multiplying it times the conjugate. I just changed that sign. So now for the top, I have to do the 2 times the 5, so that gives me a 10. And then the 2 times the negative radical 3, so that gives me negative 2 radical 3. For the bottom, this kind of falls under the last rule we were talking about. This is the whole reason we multiply times the conjugate, is you just have to do the first one times the first one, and then the last one times the last one. So radical 3 times negative radical 3 gives us a negative 3. any middle term you have there is going to cancel because you have the same numbers in front, same numbers in the second spots. So now just actually subtracting, I get 10 minus 2 radical 3 still on my top. 25 minus 3 gives me a 22 down there. So now I have to look at the 3 numbers outside of the radical. Can I reduce all 3 of those by the same number? Yes. What can I divide them all by? 2. So we got to do that. 10 divided by 2 is 5. 2 divided by 2 is 1. So I got 1 radical 3. And then 22 divided by 2 gives us 11. So that ends up being our final answer. Alright, last one in our notes here. What are we going to multiply times? Bottom, but what do we switch about the bottom? Make it a plus. So we're going to do 4 plus the square root of 5. Multiplying times the conjugate. So we got to multiply out in the front. So I'm going to do 3 times my 4. And then 3 times my square root of 5. So that gives me 12 plus 3 radical 5. Then I got to multiply with my radical 5. So radical 5 times 4 is a plus 4 radical 5. Radical 5 times the radical 5 is just a 5. But for the bottom, and again, the whole reason we're multiplying times the conjugate is it's just going to be the 4 times the 4 and the negative radical 5 times radical 5. So that makes that negative 5. So let's clean this up a little bit. So for our numerator, 12 plus the 5, that gives me 17. And then 3 plus the 4 gives me a 7 radical 5. And then in the bottom, the 16 minus 5 gives us 11. So now, is there a number that goes into 17, 7, and 11? Nope, because those are all primes. So there's nothing we can reduce that to. So that's going to be our final answer there.